Hello everyone, my name is Antun Meglic. I'm a PhD student at the Faculty of Electrical Engineering, Mechanical Engineering and Naval Architecture at the University of Split, and today I'm going to present you a Wavelet multi-scale analysis of wind turbine smoothing effect and power fluctuations. The outline of this paper is the following. First, we are going to start with the introduction. Then in section 2, we are going to explain the application of wavelet transform to the analysis of wind power fluctuations. And then in section 3, the methodology of this work is going to be introduced. At the section 4, we have the results of the smoothing effect in wind farms, and finally conclusion in section 5. Recent increase in interest for collocation of wind and solar PV plants raises the questions related to power fluctuations and their impact on power curtailment losses. The investigation is needed to quantify the reduction in power fluctuations that we can expect in wind farms when aggregating multiple wind turbines, which we call the smoothing effect. Our objective is to analyze power fluctuations and smoothing effect in wind farms for multiple wind turbines and various frequency bands. The way we analyze power fluctuations in wind farms is by using the Maximal over discrete wavelet transform, abbreviation MODWT, which when applied to wind power time series decomposes the wind power time series to multiple scales, each representing certain frequency band. So starting from scale 1, we have the highest frequencies contained within the wind power time series, and up to the last scale, which represents the slowest fluctuations contained within the signal. The important property that MODWT has is that it is variance preserving decomposition. This is the methodology that we used throughout this paper. We started with the power data collection from 3 operational wind farms. Then we aggregated the power of n wind turbines and normalized the power time series to obtain comparable results. After that, at the step 3, we applied wavelet transform to the power time series of the wind turbines, and then we calculated the variance for each scale. And finally, we obtained the results of the smoothing effect for n wind turbines relative to a single wind turbine, which we call relative variance. These are the results of the smoothing effect in wind farms for the first 6 scales, which represents the highest fluctuations within the wind power time series. On y-axis, we have a relative variance, and on x-axis, we have the number of wind turbines. What we can see from these graphs is that for each additional wind turbine that we add, the variance is going to drop by a function that can be represented by 1 over n, where n is the number of wind turbines. As we move on to higher scales, we are actually moving to lower frequencies. And here are the results for the scales 7 to 12. What we can see is that as we move on to higher scales, the drop in variance is becoming less significant. And finally, at the scale 15, we can see that the variance is, as we add each additional wind turbine, is not dropping as much, so we can say that the smoothing effect ends at the scale 15. To conclude, the variance of aggregated normalized power time series is reduced by a factor 1 over n for power fluctuations with periods up to 5 minutes. As we move on to higher scales, the level of smoothing will depend on the wind spatial correlations. And finally, the smoothing effect we've seen is still active up to 13th scale, which corresponds to the periods of fluctuations up to 4.5 hours. Thank you for your attention.